In our last class, we were discussing about the discrete Fourier transform, and we had discussed its role as far as either an orthogonal discrete Fourier transform or an orthonormal discrete Fourier transform goes. And we had described that we will work with the non-normalized version of the discrete Fourier transform. And we had given all that the definitions, but now what we want to do is step away and talk about what is the relationship of the discrete Fourier transform to the frequencies, the discrete frequencies of the sequence of which we are calculating the discrete Fourier transform. In all orthogonal transforms, it's not always easy to draw an intuitive understanding of what does that transform stand for. But for the case of DFT, it is a rather simple exercise. So in this class, we'll try to understand that. So just to remember, we are interested the DFT of a sequence xn, which is not equal to 0 for n 0, 1 up to n minus 1. We had defined that as x of k summation n equal to 0 to n minus 1 x of n w of n kn, okay, where we had defined wn as e to the minus j 2 pi over n. And this is our analysis equation, and we had similarly given a synthesis equation, our xn. The synthesis equation was exactly the same. We have 1 over n, and we have conjugation k equal to 0 to n minus 1 n minus 1 x of k w of n minus kn for n equal to 0, 1 up to n minus 1, and this is for k equal to 0, 1 up to n minus 1. And what we are interested in is figuring out how is this, what is the discrete time Fourier transform interpretation of it? Is there any relationship of the DFT sequence to perhaps the DTFT of the sequence we started with? Okay. And to understand that relationship, we will have to go to the definition of discrete Fourier series, understand the discrete Fourier series, and then relate effectively discrete Fourier transform to discrete Fourier series. So the plan we have is we want to understand discrete Fourier series we want to relate that to, we want to understand the relationship of that to discrete time Fourier transform, and we want to understand the relationship of the discrete Fourier series to the discrete Fourier transform. And basically through this, we will be able to talk about what is the relationship between DFT to DTFT. Okay, so I'll be using their short forms. It's important we stay with them. DFS I will be using for discrete Fourier series. DFT I will be using for discrete Fourier transform. And our goal is relate DFT to DFS and DFS to DTFT. And through that, we will understand the role of DTFT and DFT, the relationship with each other. Okay, so what is discrete Fourier series? As all Fourier series go, whether discrete or continuous, discrete Fourier series is defined for periodic sequences. So it's discrete, we are talking about sequences, but DFS is defined for a periodic signal or sequence. And since in the following we'll be juggling between non-periodic sequences and periodic sequences, we'll be using tilde to represent a periodic sequence. Okay, so it's periodic sequence xn, and it has period with period of capital N. Okay, what this means is, since it's periodic, that x tilde of n equals x tilde of n plus Rn for all little n and little r. So it's periodic with period n. Now, we know from the Fourier series in the continuous time, if you are given a periodic signal, then the continuous Fourier series, for example, tells us that we can represent that signal as a linear combination of an infinite number of harmonics. Okay, so we know if we had, for example, if we have periodic x tilde of t, then the Fourier series tells us, which we all have covered in our undergraduate, is that x tilde of t is this summation of e to the j 2 pi k t over capital T, where capital T is our period, and we go from k minus infinity to infinity. Right? And we call these the Fourier series coefficients. So it's the same idea. We won't go into the details, but if you are given a discrete sequence which is periodic, then you can represent that according to the discrete Fourier series. You can represent that as a linear combination of harmonics. Okay, so we have a periodic signal x tilde of t with period n. The claim is we can represent that as linear combination of these harmonics, which I'm going to call x tilde of k and e to the j 2 pi over n kn. And right now I'm not going to put the order of summation where it goes from. Right? It's exactly the same thing. These x tilde of k, we'll call them the discrete Fourier series coefficients. It's harmonics of e to the j 2 pi over n. So, and the n is the period here, capital T was the period, right? So it's exactly analogous to the continuous Fourier series that we have studied. Now, the distinction comes in what should be the index of summation of these harmonics. Okay, so while in continuous time you have an infinite number of harmonics, right? You can have k equal to 0, 1, 2, 3, 4, whatever, 100 hertz, 200 hertz, 400 hertz, keep on going. Well, in discrete time, there are only n harmonics that are available to us. So if I define ek of n as e to the j 2 pi k over n times n, right? And if I define ek plus some multiple of capital N, ek plus Rn of n. Okay, so this is a complex exponential with frequency of, so this has a frequency of omega k equal to 2 pi over n times k. This has a frequency of omega k equals 2 pi over n times k plus Rn. Okay, so it is e to the j 2 pi k plus Rn over n times little n. And of course, you can do that. You multiply that, you get e to the j 2 pi over n. That is simply equal to 2 pi k over n, and the other factor just becomes 1, right? So because of the periodicity of these discrete complex exponentials, this ek plus rn equals, so this is equal to ekn. So in discrete time, you effectively have only n harmonics instead of an infinite number of harmonics. So actually the summation here, you can put any consecutive k numbers. Okay, I could put actually this to be k equal to minus n minus 1 and consecutive n numbers. So I can put k equal to 0 to n minus 1. I can have k equal to n to 2n minus 1 and so forth. Any consecutive n numbers will, any consecutive n integers will work, because after that the frequencies are the same. If you take any discrete frequency e to the j 2 pi k over n times n, add another multiple of n, you get back that same one. Okay? So this is not uniquely defined in terms of indices of k. The convention we follow is that k, we take it to be 0, 1, up to n minus 1. Okay, so I can define my x tilde of n in that case to be summation k equal to 0 to n minus 1 x tilde of k e to the j 2 pi k over n times n. Okay? But I want to be very clear that it doesn't matter which summation I pick, as long as I take a summation of n contiguous integers. Okay? So according to the discrete Fourier series, I can write my x tilde of n as 1 over n summation k equal to 0 to n minus 1 x tilde of k wn minus kn. The question is, what are these Fourier series coefficients? Now, to compute that, we just rely on the orthogonality of the harmonics. So it is not difficult to see that if I multiply two harmonics and sum them up over one period, so if I do ER conjugate of n times EKN, which is 1 over n summation n equal to 0 to n minus 1 e to the j 2 pi r over n times n conjugate and e to the j 2 pi n k over n times n. Well, it turns out that this is equal to 1 as long as k minus r is equal to some multiple of the period, an integer, okay, and it's 0 otherwise. Effectively, if k and r are related to each other by a periodic shift, then this is 1, right? Because any periodic, if I just add in the frequency a multiple of n, I get back that same frequency essentially. So as long as this, instead of writing, I'm not writing k equal to r, I'm writing k minus r equal to mn, or k equal to r plus mn, right? So if they are related by this periodic relationship, then it is 1, because then it's the same frequency. Otherwise, they are 0. Okay, so any two different frequencies, if you multiply them, add them up, you get 0 with the conjugation. Okay. So if we do that, if we keep that in mind, and we just now try to write this expression, n minus 1 x tilde of n e to the minus j 2 pi over n times Rn. And I'm now take R to be any number between 0 up to n minus 1. Okay. So in this expression, I will put in the Fourier series formula that I had evaluated earlier for x tilde n. So I'm going to put this value of x tilde n here. If I do that, I get n equal to 0 to n minus 1, 1 over n, summation k equal to 0 to n minus 1, x tilde of k e to the j 2 pi k over n times n. And I have this other exponential e to the minus j 2 pi r over n times n. And now I just expand that. I change the order of summation, take the summation over k outside. Since this x tilde of k is also not a function of n, I keep that with it. X tilde of k. I get 1 over n summation n equals 0 to n minus 1. And I just now add the two exponents. So it's e to the j 2 pi over n k minus r times little n. Now, by the property that we have discussed earlier, this whole thing will be non-zero only for the case when k equals to r. Right? I'm fixing my r. Now, I have talked about this expression that if you multiply two exponentials, which is this, right? So I can just write this in the same form to make it easier. N equal to 0 to n minus 1 e to the j 2 pi over n k minus r n. So if you compare these two expressions, and based upon what we have written, right, this whole thing will be 0 for all k except k equals r. So the only term that will survive here, everything else will be multiplied by x tilde k will be multiplied by 0, except x tilde k when k equals r. Okay. So that will be equal to x tilde of r only. Everything else will be 0. So that gives you the expression for computing the Fourier series coefficients in the discrete time, the discrete Fourier series coefficients, which is just take x tilde n and multiply it with e to the minus j 2 pi over n Rn, n equal to 0 to n minus 1. Okay. And it's easy to see that this x tilde r, or x tilde k as we will now call them, because that's just a dummy variable, x tilde k, the discrete Fourier series coefficients, are then given by x tilde of k equals 1 over, not x tilde of k equals n from 0 to n minus 1, x tilde of n e to the minus j 2 pi over capital N times Rn. and k equal to 0, 1 up to n minus 1. And you can take k after n minus 1 too. It's just going to be periodic. It's easy to see. So that's why I have the x tilde written on it. So just like the sequence, you started with the sequence being periodic, the discrete Fourier series coefficients end up being periodic also. So the discrete Fourier series is given for periodic sequences, and the discrete Fourier series coefficients end up being periodic also. Okay? And in keeping with the earlier terminology that we use, we can write that x tilde of n has a discrete Fourier series pair x tilde of k, and this x tilde of k corresponds to our analysis equation, and this x tilde of n corresponds to our synthesis part. So let's just do a simple example to help us understand this part of the discussion is all in chapter 8 of your text. Okay. So just look at example 8.1 because we'll need it later. So it's a good exercise to compute the discrete Fourier series coefficients of a simple periodic signal. So example 8.1 in your book says that you are given x tilde of n is an impulse train in discrete time. So it's r minus infinity to infinity delta of n minus rn, which means that it is 0 for n equal to n multiple of n, r an integer, and 0 otherwise. Okay, so just a simple periodic train with at 0 everywhere except multiples of n. And similarly here, minus n, and it keeps on going. Okay? And we are interested in computing the discrete Fourier series coefficients of this. So the discrete Fourier series coefficients x tilde of k, they are simply given by the formula above, n equal to 0 to n minus 1, x tilde of n, e to the minus j 2 pi k over n times n. That is simply, so this, the only non-zero between, we are taking the summation between 0 and n minus 1. So the only non-zero is at 1. For that we get 1. Okay. So only at n equal to 0, which I multiply that, I get 0. So this means that my discrete Fourier series coefficients are all 1 all the time. Okay. So if I want to plot my discrete Fourier series coefficients, they will be just this sequence. Zero, 1, minus 1, and so forth. Okay. So it's important for us to keep this in mind. We'll come back to it sometime later. Okay. There are other examples in your text with a couple of other examples that you can compute this discrete Fourier series coefficients just to get some exercise in it. So let's look at some properties of the discrete Fourier series, which are the same kind of properties that you have seen in other transforms and series. So discrete Fourier series properties, most of them are pretty trivial. The first property is that of linearity, which means that if you have one function, if you have one sequence with periodic and it has discrete Fourier series x1 tilde k, and you have another one x2 tilde n with discrete Fourier series x2 tilde k, then you can add them up. You can take any linear combination of them, a1 x1 tilde n plus a2 x2 tilde n. Okay. As long as both these sequences have the same period. So that's the key assumption. If they both have periods n, and then you add them up, of course you add two sequences with period n, you get back another sequence with the period n. Okay? So if you add them up, their Fourier series coefficients are simply going to be the linear combination of their individual Fourier series coefficients. And it's rather trivial to show using just the definition of the discrete Fourier series coefficient, so we won't try to prove that. The second property is that of shift of a sequence. So if you are given a sequence x1 tilde of n, which has a discrete Fourier series coefficients x1 tilde of k, and let's say you shift the sequence by an amount. Again, if you are given a periodic sequence and you shift it, it remains a periodic sequence. So you can talk about doing the Fourier series of that periodic sequence, and that is related to the periodic sequence, the Fourier series of the original sequence through a phase shift. So the phase shift is given by WNKM, x1 tilde k. Okay. Again, rather simple, just by doing a change of variable in your original definition of your Fourier series, and you will get back your answer. So you won't be trying to prove that. The third property is that of duality, which says because of the similarity, if we look at our analysis and synthesis equations, if I remind you of the analysis and synthesis equations, we have x tilde of k equal to summation n 0 to n minus 1 x tilde of n e to the minus j 2 pi over n kn, and x tilde of n is simply 1 over n k equal to 0 to n minus 1 x tilde of k e to the j 2 pi over n kn. If you compare, there is just a factor of 1 over n between the two, and the only difference is this conjugation. Right? So you expect, since given the similarity between the two, you expect that there will be some sort of duality existing between the Fourier series coefficients and the original sequence, with the fact that you have to keep track of this scaling factor. Okay? And so what the duality property says is that if you have a discrete Fourier series of x tilde n, and now if you take that x tilde of k, and you assume that to be your time sequence. So if you take that and assume that to be your time sequence, and you compute discrete Fourier series coefficients of that, that will come through, that will be given through this x tilde of n, with the difference that there is, of course, the scaling factor of capital N, and there is a time reversal. Okay. There's the usual duality property that you have been seeing in the discrete time Fourier transform, the continuous time Fourier transform. It's the same thing. There's a factor of n because of the fact that we are defining our discrete Fourier series with this factor of 1 over n. Okay. There are other symmetry properties which are listed. They don't teach us anything terribly new, so I won't spend more time any time on that too. There's so given in the text. Perhaps the most important property of the discrete Fourier series is that of periodic convolution, and we'll spend some time on that. So the assumption is that we have two sequences, x1 tilde n, with Fourier series coefficients x1 tilde k, x2 tilde n with discrete Fourier series x2 tilde k, and both have same period n. Then we define periodic convolution between these two periodic signals, which is defined just like the convolution, with the difference being that we take the summation only over one period. Okay, so periodic convolution, let's call that sequence x tilde of n. That is defined as, so it's given by the same expression as you see in your original convolution. Okay. You take one sequence, you flip and then shift the other sequence, so it's the same flip and slide rule. The only difference is what happens to the summation index. So in the canonical convolution, you sum from minus infinity to infinity, right? If it wasn't periodic convolution, then you will be saying take m equals minus infinity to infinity. In periodic convolution, we will say just take the sum over one period. And in general, will be taking the sum over the principal period from 0 to n minus 1. Okay. So if you define your periodic convolution like this, then the Fourier series of that is simply given by multiplication of the discrete Fourier series coefficients of the individual sequences. And you can check that it is indeed commutative. You can switch the role of these two. It won't matter. It's exactly the same as in convolution. Okay, you can fix one sequence, flip the other and slide it, or flip or fix the other sequence and flip and slide the first one. It doesn't matter. Okay, the main difference is that you want to take summation over one period rather than over the entire duration. Okay. Now, let's look at the proof of that. So, define x3 tilde k, which is the discrete Fourier series coefficients of the sequence x3 tilde k, using the definition of the discrete Fourier series that is n equal to 0 to n minus 1 x tilde 3 of n e to the minus j 2 pi over n kn. Okay. Now we just plug in the value of x3 tilde n to n minus 1 summation m x1 tilde m x2 tilde n minus m e to the minus j 2 pi over n kn. Now I'm just going to change the order of summation. So I bring the second summation outside. I carry x1 tilde m with it. Okay. And I have n equal to 0 to n minus 1 x2 tilde of n minus m e to the minus j 2 pi k over capital N times n. Now this is just, if we think of this, we are just taking the discrete Fourier series coefficients of a sequence which is shifted by m. Okay. So we did the shift property of the discrete Fourier series earlier, right, which said that if we compute the discrete Fourier series coefficients of a shifted sequence, they are related to the non-shifted sequence by a phase shift. So this means that this whole thing is nothing but a phase shift WNKM times the Fourier series coefficients of x2. Okay. So just let's write that down. We have summation m equal to 0 to n minus 1 x1 tilde of m WNKM x2 tilde of k. Okay. And of course this x2 tilde k doesn't depend upon m, so I just bring that out. x2 tilde of k, I have summation m equal to 0 to n minus 1 x1 tilde of m WNKM. Okay. Now this is nothing but the discrete Fourier series of x1 because little m is a dummy variable. So that will become x2 tilde of k times x1 tilde of k. Okay. So indeed, if we multiply the discrete Fourier series coefficients, that is equivalent to taking periodic convolution in the time domain. Okay. And because of the duality property that we did earlier, we can actually now state it the other way around too, which is that, so by duality, I can also write a result like the following. So if I multiply two periodic sequences in time, by duality, it will follow that the discrete Fourier series coefficients will be given by periodic convolution of the discrete Fourier series coefficients of individual ones. So if I say I multiply the sequences now in time, okay, then the discrete Fourier series will be given by 1 over n summation L equal to 0 to n minus 1 x1 tilde of L and x2 tilde of k minus L. Okay. Now you can, so here is an example of what periodic convolution looks like. It's exactly the same setup. You are given two sequences, x2 tilde m, x1 tilde m. You are going to, so we are now fixing x1 tilde m. We first flip x2 tilde m, okay? And then are going to slide that. So we slide it by different amounts, and then we multiply the slided one with the original one and add them all up. You should keep this picture in mind because later we'll come back to circular convolution, which is effectively related to this notion of periodic convolution. The detailed properties of the discrete Fourier series are they are pretty similar to any Fourier transform, discrete time or continuous time you have done with the appropriate modifications. We have covered some of them. So one is this linearity property. You have this sort of duality, time shift, and this sixth property again follows by duality. You have the periodic convolution property 7. You have this property 8, which also follows due to duality. There are other ones which relate to, for example, symmetry, which we haven't covered, but they are simple to derive. They are ones that become, you can say a few more things if you have a sequence which is real valued, okay? But we won't spend time on this. These are listed in your text. There is table 8.1 in your text, so you can go and spend some more time on it. Okay. Having described the discrete Fourier series, our goal now is relating this discrete Fourier series of a periodic sequence to the discrete time Fourier transform of one period of that sequence. Okay. So our goal is relate discrete Fourier series of a periodic sequence to the discrete time Fourier transform of one period of that sequence. So we are saying that x tilde of n, the way we have written our Fourier series, is given by 1 over n and linear combination of these harmonics where the weights of the linear combination are given by my coefficients, w, n, k, n, and I have k equal to 0 to n minus 1. Now what it means is that, effectively speaking, we have that x tilde of n is made up of frequencies 2 pi k over n, okay, where k goes from minus infinity to infinity. There are only n distinct frequencies, but I can think of my x tilde of n as made up of all these frequencies going from minus infinity to infinity. Okay. So without going into the technical details, if I say that I have a sequence which has, I'll try to give this analogy which is non-rigorous, okay, just to make you understand. So let's say I have x of n, which is w of n kn. And I ask what is the discrete time Fourier transform of that. That is just an impulse. Okay. So the discrete time Fourier transform of this, the DTFT of this, which is x of e to the j omega, there is of course 2 pi. That is simply given by an impulse at location 2 pi k over n, right? And of course it's periodic repetition. So that is given by simply summation of delta of omega minus 2 pi, okay, k over n minus 2 pi r. If I want to plot its DTFT, that will be just one impulse at, if this is 0, I'll only look at minus pi to pi. Okay, I will have an impulse with height 2 pi, and the location of this impulse will be little omega equal to 2 pi k over n. Now I'm claiming that my signal is made up of all these frequencies. So that means that now I have impulses at all of these locations. So the Fourier transform of x tilde of n, okay, in general, remember, we cannot define in a more rigorous fashion discrete time Fourier transform, just like continuous time Fourier transform for a periodic signal cannot be defined, technically speaking, because they have infinite energy. You can't, like if you're talking about continuous time signals, you can't integrate them to have finite energy. Right? They don't belong to L2R. Similarly, periodic sequences are not going to belong to L2Z. So, but we can take this sort of non-rigorous view that since my signal consists of all these frequencies, so each of the frequency I'm going to represent that through an impulse, right, at the right location. So I have frequencies at the 2 pi k over n, and what is the height of each frequency? The contribution of each frequency is x tilde k. So for example, here if I multiplied it with 2, right, then I should have multiplied this with 2 also, right? Because that meant that the contribution of this frequency is twice the normal contribution. So similarly, if I think of this, I have 1 over n comes from this, 2 pi comes because of the fact that we are dealing in radians. So I have 2 pi over n summation k minus infinity to infinity. X tilde of k is the area of my impulse times delta of omega minus 2 pi k over n. Okay, so it's effectively my Fourier discrete time Fourier transform. The way I'm representing that is through impulses at locations 2 pi k over n. At 0, I have an impulse at 0 with a height with the area of 2 pi over n x tilde of 0. Right? I have an impulse at 2 pi over n with a height of 2 pi over, or area of 2 pi over n x tilde of 1. Okay, and of course it can go negative if x tilde of 1 is negative. I have 1 here, minus 2 pi over n, right, and so forth. Okay, so you either take it as the way we are going to define the discrete time Fourier transform of discrete periodic sequences, or you can think of the way I've tried to motivate it, whichever way works better for you. But effectively, if we are given a periodic sequence with represented in this discrete Fourier series form, then effectively what we are saying is that the DTFT of that can be expressed as 2 pi over n times k minus infinity to infinity x tilde of k delta of omega minus 2 pi k over n. Okay. Now let's assume, so we'll work with this definition you can treat this as a definition. We'll work with this definition of the discrete time Fourier transform of a periodic sequence. Okay. Keep this definition in mind. We'll come back to it. We'll come back to it later. Now let's talk about, assume that now we are given an aperiodic sequence xn, okay, that is finite duration and without loss of generality we are going to assume that xn is not equal to 0 only for n from 0, 1 up to n minus 1. Okay. So I am given a sequence which is aperiodic, and what I want to do is compute a periodic extension of that sequence. So using that xn, I define what we call periodic extension of this xn as x tilde of n equals to summation r from minus infinity to infinity x of n minus Rn. Okay, so just take your sequence and start replicating it after every n steps. So if my sequence was, for example, 0, 1, and let's say my n is 4, right? Then I just start repeating it after every 4 samples. Okay. So this part from here to here is my xn, which I'll be calling principal period. And the rest are periodic extensions of that. Okay. So this is the mathematical expression for representing that periodic extension. Now, what is one way of writing that periodic extension is basically, it's similar to if you have remember convolution with a discrete impulse, right? If you convolve with a discrete delta function, what happens to the function? It just gets shifted there, right? So if I multiply xn with delta of n minus Rn, I get convolve xn with delta of n minus Rn, I get x of n minus Rn, right? Due to the convolution property of my delta. So I can write this periodic extension as follows then. Instead of writing xn, x of n minus Rn, I can also write it as convolution with a periodic impulse train. Okay, so x tilde of n can be written as r from minus infinity to infinity. X of n minus Rn can be simply written as xn convolution of delta of n minus Rn, which I can write as xn, because convolution is a linear operator, r from minus infinity to infinity delta of n minus Rn. Okay. Now let's define that as p tilde of n. Tilde because this is periodic. This is periodic with period n. So I can define the periodic extension of a finite duration sequence by simply convolving that sequence with a periodic impulse train, with a periodic delta train. Okay? Now, I am interested in computing the DTFT of x tilde n. Okay. So I'm given x tilde n equal to convolution of xn with another sequence p tilde n, and I want to compute the DTFT, not the discrete Fourier series, but the discrete time Fourier transform, which is x tilde e to the j omega. Okay. So if I'm convolving two sequences, what do I get in time? What do I get in the discrete time Fourier transform? I get their multiplication. So I get x of e to the j omega times p tilde of e to the j omega. Okay. Now, p tilde of e to the j omega, we did that exercise earlier. We computed the discrete Fourier series of p tilde of n. Okay. Remember, this thing is just a delta train, a delta every n samples, 0, n, and so forth. And that was the example we did. So the Fourier series coefficients of that are all 1. So p tilde of k is all 1. Okay? And by the definition, so we'll now come back to this expression. We said that if you are given a periodic sequence, if you want to write down its discrete time Fourier transform, that is given by 2 pi over n times the discrete Fourier series of the sequence times delta function. Okay. So if you use that expression, then what you have is that p tilde of e to the j omega has to be equal to 2 pi over n summation k minus infinity to infinity p tilde of k delta of omega minus 2 pi k over n. But the example we did earlier in class shows that p tilde k, they are all equal to 1. Okay. So that will be equal to 2 pi over n summation of k minus infinity to infinity delta of omega minus 2 pi k over n. Now we plug that in the above expression to get the discrete time Fourier transform of x tilde n. We get x tilde of e to the j omega equals 2 pi over n x of e to the j omega k equal to minus infinity to infinity delta of omega minus 2 pi k over n. Okay. Now I'll take this inside the summation. I'll get 2 pi over n inside the summation k minus infinity to infinity x of e to the j omega delta of omega minus 2 pi k over n. Okay. Now here we have two functions getting multiplied. One is an impulse. The other is any function. Which property do we use of the impulse? The sifting property, which says that if you multiply a function with an impulse, you get back the impulse, where the area of the impulse gets scaled by the value of the function at that location. So this thing is simply x of e to the j 2 pi k over n times delta of omega minus 2 pi k over n. So we have computed the the discrete time Fourier transform of a periodic signal, okay, as a function of the discrete time Fourier transform of its principal period. Remember the steps that we took. We started with xn and we made that into a periodic sequence x tilde n, x of n minus Rn. Okay? And the question we want to ask is, so this x tilde n is now periodic. This means that this x tilde n has discrete Fourier series coefficients. The question we want to ask is, how are the discrete Fourier series coefficients of this x tilde n related to the discrete time Fourier transform of the aperiodic sequence you started with? Okay? So that's the question we want to ask. And we have been able to write the discrete time Fourier transform of this periodic sequence. Okay? Now, earlier we said that the discrete time Fourier transform of a periodic sequence should be written as 2 pi over n summation k equal to minus infinity to infinity times the discrete Fourier series coefficients of that sequence, x tilde of k. Right? So if I were given just this periodic sequence, I could have computed its discrete time Fourier transform as 2 pi over n summation k x tilde of k delta of omega minus 2 pi k over n. Okay? So this is one expression for the discrete time Fourier transform of my periodic sequence. This is another expression for the discrete time Fourier transform of my periodic sequence. The only difference is this. This means that the discrete time Fourier transform of, or the discrete Fourier series coefficients of my periodic sequence has to be these things, x e to the j 2 pi k over n. Okay? So, and what are those x e to the j 2 pi k over n? That means that this xn has a Fourier transform x of e to the j omega, and you are sampling that Fourier transform at 2 pi k over n. Okay? So to wrap it all up, if you take a sequence and you do its periodic repetition with a period n, and then you compute the discrete Fourier series coefficients of that sequence, the relationship between the discrete Fourier series of x tilde n and the discrete time Fourier transform of xn is that the Fourier series coefficients of x tilde n are nothing but samples of your discrete time Fourier transform. Okay. So assuming, for example, if we take the case of xn, so let's take the example which is example 6.8, example 8.6 in your text. That says that xn is 1 for 0 less than or equal to n less than or equal to 4 and 0 otherwise. This is just this rectangular pulse So xn is simply this thing, 0, 1, 2, 3, 4. Okay. The discrete time Fourier transform of this thing is xe to the j omega. You can compute its a rectangular pulse, so its discrete time Fourier transform is simply sine over sine. Okay. So the discrete time Fourier transform is simply e to the j minus j2 omega, which is due to the fact that I'm starting at 0. I'm not symmetric around 0, times sine of 5 omega by 2 over sine of omega by 2. Okay. And if I were to plot its magnitude, so let's plot its x of e to the j omega. The magnitude of that between 0 and minus pi and pi looks very similar to the sinc function. Okay. It's sine over sine, not sinc, because the discrete time Fourier transform has to be periodic. So the Fourier transform is given by this expression. So here is pi. So this is minus pi, and this is pi. Okay. And the height of this thing is 5. Okay. So this is the DTFT. Now let's assume that I compute a periodic extension of this thing at with some time period. Okay. So if I now compute x tilde of n, which is given by summation of x of n minus Rn. So I just take this sequence and I start repeating it after every n time steps. I will get back a periodic sequence, and that sequence is going to have some discrete Fourier series coefficients. Those discrete Fourier series coefficients correspond to the samples of this DTFT. So x tilde of k will be equal to samples of this at omega equal to 2 pi k over n. Okay. Effectively, you will divide this whole thing into every 2 pi over n intervals. So you will divide that, for example, this is 2 pi over, this whole thing is 2 pi over n. Your first Fourier series coefficient will be this, the second will be this, the third will be this, and so forth. Okay? So there is an intimate relationship between the discrete Fourier series coefficients of a periodic sequence and the discrete time Fourier transform of the principal period of that sequence. Okay? And now what in the next class we want to do is actually define discrete Fourier transform through the discrete Fourier series. And that is what will relate it to the discrete time Fourier transform. In your undergraduate, you probably just studied DFT being samples of DTFT. Okay? But that is only half true. The real definition of DFT, if you want to relate it to DTFT, comes through its relationship with the discrete Fourier series. And that is what we are trying to build on here. So today what we have done is related a sequence which was finite duration, its discrete time Fourier transform to the Fourier series coefficients of its periodic extension. Next Monday, we'll define our discrete Fourier transform in terms of that discrete Fourier series.